Okay, so again, 8.5, determinant and inverse matrices. So every matrix has what we call a determinant. Let me rephrase that. Every square matrix has a real number associated with it called the determinant. And the determinant almost always shows up on the ACT. On almost every ACT that's ever been out there, it's asked you to find the determinant of a matrix. So this is kind of a useful information today regarding the ACT. But it's also useful for finding an inverse matrix, because to find the inverse, you have to find the determinant. So every square matrix, you guys remember what a square matrix is? We talked about it the other day. The dimensions are like 2 by 2 or 3 by 3 or 4 by 4. It can only be a square matrix that would have a determinant. If it's not a square matrix, it can't have a determinant. So every square matrix has a real number called a determinant. The determinant of a matrix is denoted as, and we're going to see it two different ways. You might see it like written as DET of A, like this. That's how you're going to see it, I think, in the calculator and in Desmos. I believe you see the DET. That means the determinant. Or you'll see it as absolute value bars with an A like this. Okay. That's why I don't like it when they do absolute value bars around what's supposed to be a matrix, because I think it's confusing that way. Because when you see absolute value bars with a matrix number or letter in it like that, it really means to find the determinant of that matrix. And the determinant is just a number. And I'm going to apologize now because sometimes I accidentally say discriminant instead of determinant, but that's not what I mean. If we're talking about a matrix, I absolutely mean the determinant of a matrix. So the determinant of a 2 by 2 matrix is really easy to find. So let's talk about it. It says given A, B, C, D in this matrix, the rule to find the determinant is just you cross multiply the elements that are across like this. So A times D minus, and then you cross multiply the other two, B times C, and you subtract the two numbers that you get. So while you can do this in the calculator, and I'm going to show you the calculator button, I'm not going to try to hide any of that from you at this stage of the game. But I do think that if it's just a little 2 by 2 matrix, doing it by hand is easier and faster than even typing it in the calculator. Because like number one, I can just look at that and I know that negative 10 times negative 4 is positive 40, minus 5 times 3 is 15. 40 minus 15 is 25. 25 is the determinant that is associated with that square 2 by 2 matrix. I don't know that I could have gotten to second matrix yet and typed all that in as fast as I could have just done the math. So, and again, it's usually a 2 by 2 matrix on the ACT. So this is certainly a question on the ACT that could be a time saver. You know, it's like 60 questions in 60 minutes, and that certainly didn't take me a minute. So if you know how to do this, it's easy peasy to just find the determinant. So again, here we'll multiply across like this, 11 times, well, we got to go the other way first, excuse me. Negative 6 times negative 2 is positive 12, minus negative 33. And we know two negatives actually make a positive, so this is 45. Go the main diagonal first. So 5 times negative 9 is negative 45, minus negative 7 times negative 5 is positive 35. So negative 45 minus 35 is negative 80. So that is the determinant associated with that 2 by 2 matrix. And then we'll go down the main diagonal first, always. Negative 16 minus 24 is negative 40. So finding the determinant of a 2 by 2 matrix, easy, no problem. Finding the determinant of a 3 by 3 matrix is a little bit uglier. And while I'm going to show you how to do this in the calculator, and you won't have to do this by hand, I think it's important for us to know how useful these calculators truly can be. So I'm going to show you how to do this. And then please don't stress out on me, and no, you're not going to have to do this by hand. But I want to show you what the calculator is actually doing, because I don't think it ever hurts us to know what the calculator is actually doing. Okay. So this is a square 3x3 matrix. And in order to find the determinant of a square 3x3, I'm going to do a similar process, but I have to add on some extra rows here to do my diagonal multiplication. So what I'm going to do is rewrite the first two columns to the right of the matrix. So I'm going to rewrite 3, -5, and 1, -7, 4, and 5. Rewrite the first two columns to the right of the matrix. Now, find the sum of the products of each downward diagonal. So we're going to look at the downward diagonals first. What do we mean by that? Well, start at the main diagonal. That's a downward, that's a downward, and that's a downward diagonal. So we're going to multiply each of those diagonals and get a number, and then we're going to add them up. Okay? So 3 times 4 times -1. That's -12. -7 times -5 times 1. That's +35. 2 times -5 times 5. That's -50. And then I add those three numbers together. -12 plus 35 plus -50. That gives me -27. So that's the down diagonals. Find the sum of the products of each downward diagonal. So product means multiply. We multiplied all the downward diagonals and then we added them up. Find the sum of the product. So we did that. Now we got to find the sum of each upward diagonal. So now I got to go up this way, and this way. I've got to find the sum of each upward diagonal. So 1, 4, and 2, that's all 8. 5, -5, and 3. So -25 times 3 is -75. -1, -5, and -7. My third upward diagonal. Those numbers multiplied together is -35. I'm going to add them up. So 8 plus -75 plus -35. That gives me -102. And then for my last step, those are the two numbers that I subtract. Okay? Subtract the upward diagonal sum from the downward diagonal sum. So -27 minus -102 is 75. That's how you find the determinant by hand of a 3x3. But of course, it's much, much easier just to do it in the calculator. So let's look at how to do it in the calculator and how to do it in Desmos. Okay, so we're going to look at how to find the determinants in the graphing calculator and how to do it in Desmos. So I'm going to go ahead and do the graphing calculator first. So if you're using your graphing calculators, if you want to pick this up, or if you're using Desmos, either one, go ahead and enter in matrix A and matrix B, and we're going to find the determinants of matrix A and matrix B. So remember, in the graphing calculator, second matrix, you're probably really good at this now. I like to just type right over what's there because it's easier than trying to clear a matrix, which I can show you how to do if you need to know how to clear one. It's a lot of buttons, but I can show you where that's at. -7, 13, -2, and -9. Again, I always like to enter them in horizontally and then go back and look at them vertically. So I got that one in under A. I'm going to put this 3x3 in under B. All right, again, I wrote them, I typed them in horizontally, so I'm going to check vertically now real quick just to make sure all of my negative signs are there like they're supposed to be there. Okay, in the graphing calculator, once you have them in, and then we'll just go back to the home screen, in under matrix A or matrix B, if I want to find, it says find the determinant of matrix A. So go back into second matrix and go over to math, where it says math in the graphing calculator, and number 1 says DET. So if you just hit enter, it puts determinant on your home screen. And then, of course, you have to tell the calculator what matrix you want to find the determinant of. So second matrix, and I'll just go ahead and choose A. The determinant of matrix A is 89. And if I want the determinant of matrix B, I do it again. Just go second matrix and over to math. Okay, that's where you do a bunch of the matrix operations. Number 1 is determinant. And then you have to tell the calculator which matrix you want to find the determinant of. So I choose matrix B, and the determinant of matrix B is 1,276. So that's how you do it in the graphing calculator. If we're going to do it in Desmos, let me just pull this Desmos screen over here, enter in a matrix, and I'm just going to enter in matrix A. I won't do both of them here. Desmos, in my opinion, is pretty easy to try to figure out what we're doing. I just want to make sure you see the button that you're supposed to push. So, all right, so -7, -2, 13, and -9. And then see down here at the bottom where it says DET, that's determinant of A. And there's the 89. Okay? Is everybody okay if I don't do B and Desmos? Are we all good? Okay. I know it's pretty self-explanatory. I just wanted to make sure everybody was good. All right, so we'll write these down. This one is 89, and this one was 1,276. All right, so now let's talk about inverses, okay? Two n by n matrices are inverses of each other if and only if their product, which is their multiplication, like when you multiply them together, so their product, and it has to be in both orders, like going both directions, A times B and B times A, in both orders, is the identity matrix. We got to talk about that. Okay, their product in both orders is the identity matrix. Well, what is the identity matrix? Let me show you. The identity matrix, we'll write it over here. All right, it's ones down the main diagonal and zeros everywhere else. Ones down the main diagonal and zeros everywhere else. For example, the 2 by 2 identity matrix looks like this. Ones down the main diagonal, zeros everywhere else. The 3 by 3 identity matrix looks like this. Ones down the main diagonal and zeros everywhere else. So we're going to check and see if matrix A and matrix B are inverses of each other. And we're going to check and see by seeing if when I multiply A times B, I get the identity matrix. And if I multiply B times A, I get the identity matrix. Okay? And I don't care if you guys want to do this by hand or if you want to enter them in the calculator or Desmos real quick. It doesn't matter to me. Remember, matrix multiplication goes pretty quick if it's just a 2 by 2. It's no big deal. This would be -5 plus 6. That's definitely a 1. You can enter them in the calculator if you want to do it that way. Row 2, column 1 is going to be negative 2 plus 2, which is 0. Row 2, column 1 is going to be 15 minus 15, which is 0. And row 2, column 2 is going to be 6 plus negative 5, which is 1. So that one got us the identity matrix. Let's do it the other way now. B times A. Okay, and if you enter them into the calculator or Desmos, you need to multiply A times B, and then you need to swap it and multiply B times A. Remember in section 8.4, we learned that these are not normally commutative. They're only going to be commutative if it's the identity, if it's their inverses of each other. So B times A, let's do that way. So row 1, column 1. So negative 5 plus 6, that's 1. Row 1, column 2 is let's see, row 1, column 2. We've got 10 minus 10, yep, that's 0. Row 2, column 1, negative 3 plus 3. Row 2, column 2, 6 minus 5 is 1. So yes, A and B are inverses because B times A and A times B gave us the identity matrix. Now, I'm going to show you here in just a minute how to find the inverse of a matrix. Because you might be asking yourself, well, how do I know? How did they get that B is the inverse matrix of A? Well, we're going to talk about it here in just a minute. So first, can we prove that they are? And then we'll go back and show how we actually found them. So let's try these guys and see if these guys are inverses of each other. R times S. So negative 8 times negative 6 is 48 plus 48. Uh-oh, that's 96. We're not off to a very good start to get the identity matrix, are we? Negative 16 plus 15, or excuse me, minus 15 because it's a negative sign. That's negative 31. Row 2, column 1 is negative 24 minus 32, 24, that's negative 56. And 8 plus 10 is 18. Okay, that's definitely not the identity matrix. So RS, R and S, sorry, I should have said R, matrix R and S are not inverses of each other. R and S are not inverses. Okay, so if they are inverses, they have to both directions multiply to the identity matrix. Let's actually talk about how we found here matrix B, which is the inverse of A. All right, we're going to talk about that on the next page. So, do all matrices have an inverse matrix? Because like here, we said that S was not the inverse of R here. But does R have an inverse? Well, not all matrices have an inverse. The answer to that question is no. All matrices do not have an inverse. Matrix A does not have an inverse if the determinant, remember that number that we found at the beginning of the lesson today, equals 0. Super important to know that. Might be a multiple choice question or something like that where you might see it that you need to know that. Do all matrices have an inverse? No. A matrix does not have an inverse if when you calculate the determinant, it equals 0. Why? Well, because here's how you calculate the inverse of a matrix. I'm just going to do it with a 2 by 2 because you have to find the determinant. To find the inverse of matrix A, you have to do 1 over the determinant. And of course, the determinant of a 2 by 2, like no big deal, right? We're going to do this one by hand here in just a minute. But you guys remember the determinant of a 3 by 3 that we did a minute ago. That's a lot bigger of a deal. 1 over the determinant times what I like to call the swap matrix. It's kind of funny because if you look at it, you swap the positions of A and D, and you swap the signs of B and C. So the main diagonal swaps positions. The non-main diagonal swaps the signs. So the determinant can't be 0 because look right here. This is 1 divided by the determinant. If the determinant is 0, can I divide by 0? No, you can't ever. So that's why an inverse doesn't exist if the determinant equals 0, because right here to calculate it, you have to do 1 divided by the determinant. Well, all right, we're going to find the inverse of this matrix. I'm going to show you these by hand, and then I am going to show you how to do this in the calculator. But again, I don't think it hurts for us to know what the calculator is actually doing and appreciate it. So to find the inverse of this matrix, I need the determinant. Okay, I'm going to call this guy A. So I need the determinant of A. Remember, the 2 by 2 is really easy. I just do the main diagonal, 12, minus the non-main diagonal, which is -1 times -6, which is 6, which is 6. So that's the determinant. So then I take 1 over the determinant, and I multiply it times this funny swap matrix. So I'm going to swap the numbers in the main diagonal. 3 goes up here now, 4 comes here. And for the non-main diagonal, I swap the signs. So this becomes 1, this becomes 6. And then 1/6 times all of this, I do what we know as scalar multiplication. Okay, I take 1/6 times every element. 1/6 times 3 is 3/6, which is 1/2. 1/6 times 1 is 1/6. 1/6 times 6 is 6/6, which is 1. 1/6 times 4 is 4/6, which I know simplifies to 2/3. This is A to the -1. This is the inverse of A. That's how you find the inverse of a matrix. So do me a favor and enter matrix A either into Desmos or in your graphing calculator. So if I enter matrix A into my graphing calculator, it's a 2 by 2. So there it is in my graphing calculator. I'll do it in here real quick. Shoot. 4, -1, -6, 3. Okay. So in here, if I want to find the inverse of the matrix, I just hit A and then raise it up here to the -1. To the -1. Now this is in, I don't like seeing these weird decimals. I want to see my exact fractions. There we go. 1/6, 1/2, 1/6, 1 and 2/3. Is that what we got? Okay. So this notation, A to the -1, means to find the inverse. This is how you do the 2 by 2 by hand. Of course, the 3 by 3 looks much harder than this by hand, and I'm not going to ask you to do it by hand, so I'm not going to show you one, but you get the idea. 1 over the determinant times this weird swap matrix. Okay. So in the calculator, we have it in there. I'm going to quit. Back to my home screen. Second matrix, just choose A. And then the button, sorry, let me minimize this. The button that you're actually hitting for matrix is the x to the -1. If you just hit that, it raises the a to the -1 and you hit enter and it gives you the decimals. I don't want the decimals because I don't want these weird ones that you'd have to go, gee, I wonder what she wants me to round to. So math to frac and put them back into fractions. That button works even with matrices. So there's the inverse matrix using your calculator. Inverse matrices are really important. We're going to use them in section 8.6. Does anyone have any questions about how to do this in the calculator or in Desmos? Okay. All right, number 8, let's find the inverse. Did anyone try already? Did anyone try already? Let's do the determinant of, I'm going to call this one B. So -8 minus, -8. What do I get? 0. So is there going to be an inverse? No, because I can't take 1 divided by 0 times my swap matrix. Eek, can't divide by 0. So no inverse. Determinant equals 0. If you tried to do it in the calculator, I was hoping somebody told me they tried and they got an error. What did it tell you? It gave you an error, right? Gives you an error message. Good. I was hoping somebody would have tried and got an error and was brave enough to say I got an error message. Oh, when I was finding the determinant?
Yeah, so I thought you were talking about like question 8.
Oh, got it. Okay. Sorry. Yes. No. We were trying to find the inverse and we were realizing it wasn't happening there. So, all right. The rest of these notes are just practicing finding inverse matrices in the calculator. So if you want to practice a couple of these, like practice C and D and make sure you can get the inverses, I'm going to put the inverse matrices here. It wouldn't be a bad idea to check and make sure you can get the right calculator steps. The inverse of matrix C ends up -9, -11, 4, and 5. And the inverse of matrix D, I'll write it down here so you can check your calculator or Desmos and make sure you're hitting all the right buttons to find an inverse. All righty. All right.